Okay, so we've completed the counting videos, which means that we are very comfortable with, if we're given a situation, no matter how complex it is, we have a good sense for how to approach counting the number of different outcomes, whether it be the total number of outcomes or the total number of specific types of outcomes. All right, now, as I mentioned in a previous video, we didn't go as fully extensive in depth into counting as we could have gone. We didn't do a full course in combinatorics. However, we did go very deep, significantly deeper into how to count than what you would learn in a typical introductory statistics course. Okay, and the reason why we did this is because, so now we're moving on to part 4 of the statistics textbook, which is on probability. Okay, but really probability and chance aren't just some subsection of statistics. It's really an inherent part of statistics in general, in particular inferential statistics. Statistics in and of itself, making predictions, coming to conclusions, it's all centered around probabilities. That's how you're analyzing statistical data. All right, and what you're going to see is, as we go through part 4 on probability and the remaining sections of this textbook, really anything involving inferential statistics, having a strong understanding of how to count is going to make everything significantly more fruitful as we go through it. It's going to enhance your understanding of everything. And again, you'll see that as we progress through these chapters and sections. Okay, so in this video, we're going to start chapter 13. We're going to go through the opening section, which is an introduction to chance. So where like chance and probability are the same idea. It's two ways of saying the same thing. So the chance, the definition of chance is it's the possibility of something happening, kind of like the odds of something happening, or you could say the probability of something happening. Okay, so what we're doing in this opening section is just thinking about what is the meaning of chance and probability. Okay, so it says, people talk loosely about chance all the time without doing any harm. So what are the chances of getting a job, of meeting someone, of rain tomorrow? But for scientific purposes, it is necessary to give the word chance a definite, clear interpretation. This turns out to be hard, and mathematicians have struggled with the job for centuries. They have developed some careful and rigorous theories, but these theories cover just a small range of the cases where people ordinarily speak of chance. This book will present the frequency theory, which works best for processes which can be repeated over and over again, independently and under the same conditions. Many games fall into this category, and the frequency theory was originally developed to solve gambling problems. Yeah, many games, they're talking about like card games and actual games, board games or whatnot. Okay, and the frequency theory was originally developed to solve actually gaming problems. One of the great early masters was Abraham de Moivre, a French Protestant who fled to England to avoid religious persecution. Part of the dedication to his book, The Doctrine of Chances, is reproduced in Figure 1 on the next page. So yeah, what you can think about is how we as human beings interpret the idea of chance, the odds of something happening, the probability of something happening, can be very subjective. That you could have different theories of what is the root meaning of chance. It could be prayer, right? You could, if you're religious, you could think it has something to do with prayer, or maybe public opinion, or maybe how much effort was initially put in to prepare for something. So there's different probability theories, but the one that's probably the most intuitive to understand, and the one that we're going to focus on in this textbook, in this course, and the one that people are in general most familiar with, is frequency theory. Okay, and so the way frequency theory works is that if you've got some circumstance that you're trying to analyze the odds of something happening, the probability of something happening, okay, then you can always take a step back and create this hypothetical scenario in your head to think about what is the actual exact probability or chances of something happening. So what do I mean by that? What I mean is, if we wanted to think about, if you flip a coin, what are the chances, or what is the probability that you're going to get a heads? Okay, well, to truly test this, we think, well, it's 50%, right? But to truly test this and to get a legitimate mathematical answer, we would have this hypothetical scenario where you would have a machine that's going to flip the coin. I mean, I guess you could actually flip the coin yourself. That would be okay. But you're trying to do it in an unbiased way. The coin is as weight balanced as just a standard coin. Okay. And if the idea is, if you could flip this coin, have a machine running whatever, day after day after day, all day, every day, for 100 years, and you could have like an infinite number of flips, then if you divided the number of times you got heads by the total number of flips, it's going to be extremely close to 0.5. Not exactly 0.5, but extremely close. Now, but you might be thinking, well, okay, but what if you're not flipping the coin on an even surface? Or, what if there's some constraint that maybe could bias things? Well, yeah, you don't want to have any biases, but the idea of you're not flipping on an even surface, I mean, as long as you're just flipping the coin randomly somewhere every time, what's going to happen is, it's interesting to think about. If you could do like a 100 quadrillion flips of the coin, okay, and then you got the ratio of heads was 0.4, 9, 9, 9, 9, 10 nines, or 0.5, 10 zeros, 1. Okay, that's the right ratio. But if you took the number of total flips, the quadrillion or whatever, and divided it by 2, and then you compared that to the number of heads, like that would be exactly half, and you compare the number of heads to the exactly halfway point, it might be off by a million, or even a billion. But because you did the total number of flips was quintillion, or even quintillion's not infinite, right? Take quintillion and 100 quintillion and square it, right? Because you did so many flips, it's still going to be, even though you're off from being having exactly 50% heads to 50% tails by a billion, it's still, the ratio is 0.4999 100 nines, right? That's the whole idea that's how limits work. When we learn limits in calculus, that's the whole idea. You have to think about things from an infinite standpoint. Okay, and so that's the essence of how frequency theory, with respect to chance and probabilities, work. You're able to count events, count total events, and then count specific events that pertain to what you define to be success or failure. And then you could also it's very helpful to take a step back and think about the hypothetical exact probability scenario. The hypothetical, if you could do this in an unbiased way an infinite number of times, what would the resulting ratios come out to be? But again, the exact answer to the chance only comes into play when you do it an infinite number of times. Okay, now you might be thinking, well, okay, but what if it's not unbiased? You could have a weighted die, right? Here's some die. Okay, you could have it's like a cheat dice, right? It's skewed towards 3 and 5. So you've got 6 possible outcomes, but it's weighted towards the 3 and the 5. Okay, that doesn't matter though from the perspective of when you think about the hypothetical infinite experiment. That doesn't matter. That hypothetical doing the event an infinite number of times is still going to give you the exact answer. Because what would happen, right? If we had a weighted die, it was skewed towards 3 and 5. What would happen? Well, okay, if you roll the dice for 100 years, every day, all day, you have just this insane number of total rolls, and then you look at the ratios, it's going to show you, well, look, it should be the number of ones relative to the total number of rolls is like 1/6. The number of twos relative to the total number of rolls is 1/6. But again, that might seem confusing because how could it come out to be exactly 1/6 if you did it an infinite number of times and you looked at how far off is the number of twos that you got from being exactly equal to 1/6? It might be a million. You might be off by a million, but because you did it 100 quintillion to the fifth power, the ratio still it's like approaching 1/6 almost exactly anyway. So you would expect to be for each of these to be 1/6 of the ratio to the total number of rolls. But you would see that if you had a weighted die, you would see, well, look, the 3 and the 5 were more around 25%, and then the 1, the 2, the 4, and the 6 were evenly distributed with the remaining percentage. So 1/6 is like 17%. Right? So the hypothetical scenario where you make an event happen an infinite number of times will tell you if that event is skewed or weighted towards one or more of the different possible outcomes. It will tell you everything you need to know. If you do it an infinite number of times, it will tell you the exact answer. Okay? And so that's what probabilities and chances are. You have some event that you're thinking about, okay, what are the odds that this happens? What are the chances that this happens? If you could take that event without changing any of the variables associated with that event and do like a hypothetical repetition of that event off to the side, exactly how that event is, you do it an infinite number of times, and then you count the different outcomes that result and compare those as a ratio relative to the total outcomes, then you get those numbers and you put that event kind of back where it is, if it's a game or whatever it is. Not a game, it could be anything in life. Okay, then someone's going to go and do that event, right? And you can tell them, okay, here are the odds or the probabilities or the chances that this specific event happens or this other specific event happens. That's the fundamental idea of frequency theory in regards to chance and probability. Okay, so again, it says one of the great early masters was Abraham de Moivre, a French Protestant who fled to England to avoid religious persecution. Part of the dedication to his book, The Doctrine of Chances, is reproduced on the next page. So let's take a look at this dedication to Abraham de Moivre's book. So the dedication, that means de Moivre himself wrote this. It says, to the Right Honorable the Lord Carpenter, I'm not sure what that's about. My Lord, there are many people in the world who are prepossessed with an opinion that the doctrine of chances has a tendency to promote play. But they soon will be undeceived if they think fit to look into the general design of this book. In the meantime, it will not be improper to inform them that your lordship is pleased to espouse the patronage of this second edition. Okay, so espouse is just support, and then supporting the support. So, people are supporting the book, and he supports that people are backing up the book, which your strict probity, like moral standards, and the distinguished character you bear in the world would not have permitted were not their apprehensions altogether groundless. Your lordship does easily perceive that this doctrine is so far from encouraging play that it is rather a guard against it, by setting in a clear light the advantages and disadvantages of those games wherein chance is concerned. Another use to be made of this doctrine of chances is that it may serve in conjunction with the other parts of the mathematics as a fit introduction to the art of reasoning, it being known by experience that nothing can contribute more to the attaining of that art than consideration of a long train of consequences rightly deduced from undoubted principles, of which this book affords many examples. So yeah, it just sounds like de Moivre is trying to stress that his theory here on chance and probability isn't biased towards play or whatnot. It's truly like this unbiased scientific look at chance and probability. It's an art of reasoning, right? It tells you precisely what are the circumstances, regardless of if it's not promoting play or vice versa. Okay, one simple game of chance involves betting on the toss of a coin, The process of tossing the coin can be repeated over and over again, independently and under the same conditions. The chance of getting heads is 50%. In the long run, heads will turn up about 50% of the time. And what you can think about here is that as far as the probability or the odds of or the chances of getting a heads or a tails when you flip a coin, you really don't even have to think about it so much from the perspective of, is that coin just perfectly balanced in weight, top and bottom? I mean, yeah, it can't be what you would call unbalanced, but even if from a manufacturing microscopic perspective, it wasn't perfectly balanced, it's still going to work out if you did that hypothetical experiment, right? Like, you don't have to think about, I got to make sure that the surface I'm flipping the coin onto is perfectly flat, right, with no bias. Well, no, because you don't know, you're going to flip it randomly every time anyway. So when you do this, that's the usefulness of thinking about the hypothetical infinite number of doing this with like a robot or something, or even a person, an infinite number of times. It's going to give you the answer, right? As long as you're not, like, when you're flipping the coin, you're trying to do something, then it doesn't really matter if the coin is not perfectly balanced. As long as it's just a coin that came off the manufacturing currency line, right? Like any other coin. And as long as you're flipping onto you could be outside flipping onto the ground. I mean, don't go into the grass. I guess, you probably could do that, honestly. But I guess you'd probably just stay in your driveway or something, right? The general area, and just keep flipping. I mean, I wouldn't even think you'd have to actually flip it perfectly the same way every time. As long as you did it an infinite number of times with no thinking of any kind of bias in your head at all while you're doing it, then again, with an infinite number of flips, you're going to get the answer. How could you possibly not get a ratio where it's like 0.499959s or 0.5000 50 zeros and a 1 regarding the number of tails or heads to the total number of flips, right? Okay, take another example. A die is a cube with 6 faces, okay? When the die is rolled, the faces are equally likely to turn up. The chance of getting an ace, which is there's a 1, is 1 in 6, 16 and 2/3%. The interpretation, if the die is rolled over and over again, repeating the basic chance process under the same conditions, in the long run, an ace will show up about 16 and 2/3% of the time. And again, I'm going to continue to stress, I love the example, the hypothetical infinite number of rolls example, because it really, I probably shouldn't have even said that and when I first was giving this example a few minutes ago, I shouldn't have said that you've got this ideal, perfectly balanced dice. It really doesn't matter. As long as it's a dice that you buy from the store that no one has intervened with, then that's it. Roll it an infinite number of times. You're going to see that the ratio is going to be, like, as far as from the perspective of limits in calculus, it's going to be approaching 16 and 2/3%. All of these. Oh, no way. That's not going to happen. If you rolled it an infinite number of times, then it's still going to be close to 16 and 2/3%, even though the number of rolls that like to get a 3, for example, you would need to get like 1 million more 3s to actually get exactly 16 and 2/3%. You're still extremely close just because you rolled it an infinite number of times total. Okay. All right. The chance of something gives the percentage of time that is expected to happen when the basic process is done over and over again, independently under the same conditions. Yeah. So, and again, to point out, this doesn't mean this independently under the same conditions doesn't mean that you have to have an unbiased dice, a non-weighted dice. You could have a weighted dice, and it's just going to give you the correct ratios. It's just more about and ideally, you want to take what you're looking at in real life, some scenario that you're trying to think about what are the chances of the different outcomes, and hypothetically kind of pick that up and put it into this controlled environment to where you can do that event with the same weighted whatever, the same biases, the same system as it is, and just hypothetically repeat it an infinite number of times and get the results, and then compare the ratios. That's what chance and probability means, and odds, from the frequency theory perspective. That's exactly what it means. Now you might be thinking, well, we can't actually, in real life, run tests like this with an infinite number of making the event happen an infinite number of times. That's true. That's true. But it's still very useful to think about this hypothetically to start. Yes, you're going to need to have techniques and tricks for coming up with probabilities, even though you can't have there's not an infinite number of these events taking place to analyze, but it's still useful to be able to take a step back and think about the hypothetical and then go from there. The hypothetical exact percentages, exact chances, and then from there you apply the analysis that's needed to make estimates of the actual probabilities and chances. Okay, if something is impossible, it happens 0% of the time. At the other extreme, if something is sure to happen, then it happens 100% of the time. All chances are between these two extremes. So what are the chances that if you flip a coin, you get a heads or a tails? It's 100%. If you did this an infinite number of times, it's exact. This isn't 99.99999 No, it's exactly 100% because you could flip a coin an infinite number of times, and every single time you're going to get a heads or a tails. And it's a similar kind of idea when it comes to if something is impossible, it happens 0% of the time. That's the meaning of impossible, right? From the frequency theory perspective, that is the meaning of impossible. Okay, so chances or probabilities are between 0% and 100%. Here's another basic fact. Suppose you are playing a game and have a 45% chance to win. In other words, you expect to win about 45% of the time, so you must expect to lose the other 55% of the time. So the chance of something equals 100% minus the chance of the opposite thing. Yeah, and so another way of looking at this is if you take the chances of all of the events happening in the entire system and you add them up, it's gonna add up to 100%. Right? When it comes to the rolling of the dice, if you took the chances of rolling a 1, a 2, a 3, a 4, a 5, and a 6, it's going to add up to 100%. So from that perspective, you could define anything to be that chance of something happening. You could say the chance of rolling a 1 or a 3 is equal to, it's this, right? But then the chance of not rolling a 1 or a 3, you just do 100% minus the chance of rolling a 1 or a 3. And that would give you the chance of rolling a 2, a 4, a 5, or a 6. Okay? All right, example 1, a box contains red marbles and blue marbles. One marble is drawn at random from the box. Each marble has an equal chance to be drawn. If it is red, you win $1. If it is blue, you win nothing. You can choose between between two boxes. Box A contains 3 red marbles and 2 blue ones. Box B contains 30 red marbles and 20 blue ones. Which box offers a better chance of winning, or are they the same? Okay, so some people prefer box A because it has fewer blue marbles. Others prefer B because it has more red marbles. Both views are wrong. The two boxes offer the same chance of winning, 3 and 5. To see why, imagine drawing many times at random from box A, replacing the marble after each draw so as not to change the conditions of the experiment. In the long run, each of the 5 marbles will appear about 1 time in 5. So the red marbles will turn up about 3/5 of the time. With box A, your chance of drawing a red marble is 3/5. That is 60%. And then it's going to be the same idea with box B. So if you take a step back and think about this from that big picture perspective, right? If you could, the box with 5 marbles, 3 red, 2 blue, you shook it up and then took a marble out and just completely randomly and noted if it was red or blue, then put the marble back, shook it up, completely random, drew it another marble completely randomly, noted the color of that marble, right, and you did this an infinite number of times, well, there's an equal chance of picking any one of the marbles, right? And so this still might be a little bit confusing for you. You have to think about it if we did it an infinite number of times. Infinite, right? There's an equal chance of picking any one of those marbles. So with an infinite number of picks, each of the marbles is going to, if you had like a number on each of the marbles, they're going to be, the number of times you picked them relative to the total number of picks is going to be approaching 1/5. Okay, but there's 3 red marbles and there's 2 blue. So when you compare it as far as red to blue, it's going to be 3 to 5. That's going to be the chances of picking a red marble. And it's the same idea with the 50 marbles, 30 red, 50 blue. Assuming you could have, it's like you could stick your hand in that box and kind of just like mix through all of them and just grab one out, right? If you really mixed them up and did this in infinite, I'm saying infinite is so key here, an infinite number of times, each of those marbles is going to come out to, it's one in every 50 picks, you're going to pick one of those marbles. That's what the ratios are going to show. Well, since 3 out of every 5 of the marbles are red, that's going to be the ratio of your chances of picking a red marble. That's going to be the ratio of the number of red marbles you picked relative to the total number of marbles. The same exact odds or chances in either of the 2 boxes. Okay, so the ratio is the same in both boxes. De Moivre's solution for this example is given in figure 2. So De Moivre says about this type of problem, the probability of an event is greater or less according to the number of chances by which it may happen, compared with the whole number of chances by which it may either happen or fail. Wherefore, if we constitute a fraction whereof the numerator be the number of chances whereby an event may happen, and the denominator the number of all the chances whereby it may either happen or fail, the fraction will be a proper designation of the probability of it happening. Thus, if an event has 3 chances to happen and 2 to fail, the fraction 3/5 will fitly represent the probability of its happening and may be taken as the measure of it. The same things may be said of the probability of failing, which will likewise be measured by a fraction whose numerator is the number of chances whereby it may fail, and the denominator the whole number of chances, both for its happening and failing. Thus, the probability of the failing of that event, which has 2 chances to fail and 3 to happen, will be measured by the fraction 2/5. The fractions which represent the probabilities of happening and failing being added together, their sum will always be equal to unity, since the sum of their numerators will be equal to their common denominator. Now, it being a certainty that an event will either happen or fail, it follows that certainty, which may be conceived under the notion of an infinitely great degree of probability, is fitly represented by unity. So the number 1. These things will easily be apprehended if it be considered that the word probability includes a double idea. First, the number of chances whereby an event may happen. Secondly, of the number of chances whereby it may either happen or fail. So yeah, here's just a summary of everything we've talked about in this entire video. I mean, I wouldn't call it a summary. This is like the original statement of everything we're talking about in this video. So we're sort of summarizing this. Okay, many problems, like example 1, take the form of drawing at random from a box. A typical instruction is draw 2 tickets at random with replacement from the box. So draw these 2 tickets at random with replacement. So yeah, here's a great example of why it's going to be really helpful that we learned how to count, because now we understand exactly what this means with replacement, right? We know what with replacement means: combinations with repetition, permutations with repetition, etc. So all this is really coming down to is we're just counting the number of total outcomes and then comparing that to another count based on something we're analyzing, whatever we choose, right? Whatever we deem to be a success or failure. That's what it all comes down to. So here we're picking from 3, right? We're picking 2 with repetition. So, okay, we have to ask, is this a combinations or a permutations with repetition problem, right? If it's permutations, then it's just going to be 3 times 3. If it's combinations, then we have to use the whole combinations with repetition formula. So we can count the number of what we define to be successful outcomes and then count the total outcomes and determine probabilities, chances. So this asks you to imagine the following process: shake the box, draw 1 ticket at random, equal chance for all 3 tickets, make a note of the number on it, put it back in the box, shake the box again, draw a second ticket at random, equal chance for all 3 tickets, make a note of the number on it, and put the second ticket back in the box. The contrast is with the instruction, so you could draw 2 tickets at random without replacement from the box, right? In that case, it would be just a standard kind of combinations or permutation problem, depending on if order matters or not. It probably doesn't matter, so you would do, if order doesn't matter, then the number of ways you could choose 2 tickets from 3 would be 3 choose 2. Okay? The second instruction asks you to imagine the following process: shake the box, draw 1 ticket at random, equal chance for all 3 tickets, set it aside, draw out a second ticket at random, equal chance for the 2 tickets left in the box. Yeah. Okay, so here they kind of summarize this, the difference between drawing with or without replacement. 2 draws are made at random. Yeah, so we are very comfortable now with what they're talking about here, with and without replacement, right? We can count any of this stuff. Okay, so when you draw at random, all the tickets in the box have the same chance to be picked. Right, so you're making an assumption here that truly all the tickets have the same chance to be picked. And if that's your desire, if you're trying to set something up or whatnot, then you want to do the best you can to set it up that way. But it's still important to think about how you could still hypothetically test this. If you could kind of take this system you have off to the side and repeat the event an infinite number of times, then it would show you if it's truly random or not. Or if you do, for some reason, have a bias where you keep picking a certain ticket for some weird reason, you do it an infinite number of times, and it's not, in this case, it should be 33, 1/3 to 1/3 to 1/3, so 33%. But for some reason, you keep picking another ticket 38% of the time. If you could do this hypothetical test, it would show you that. This hypothetical infinite test. Okay. Let's go through these exercises now real quick. A computer is programmed to compute various chances. Match the numerical answers with the verbal descriptions, which may be used more than once. Okay. So, this first verbal description, this is as likely to happen as not. That's going to be 50%. Okay. This is very likely to happen, but it's not certain. Very likely to happen, but not certain. So anything close to 100%, but not exactly 100%. So this won't happen. 3. This may happen, but it's not likely. Okay, so just a low percentage. This is C. This will happen for sure. Okay, V, 100%. There's a bug in the program. All right, that would be the 200% and the minus 50%. How can you calculate a chance of minus 50% or 200%? 200% is suggesting that it's like you flipped a coin 10 times and you got 15 heads. I guess that would be 200. Is that 200%? No, you got 20 heads. You flipped a coin 10 times, you got 20 heads. It makes no sense. Minus 50% is like you flipped a coin 10 times and you got negative 5 heads, right? No, we're talking about discrete outcomes here. These integers, positive integers, or 0. Okay, a coin will be tossed 1,000 times. About how many heads are expected? All right, well, 500. That would be our best guess for how many heads there's going to be. Now, there's the odds of actually getting exactly 500 heads are low, but that's our best guess. How could we argue without any more information that we should guess 480 heads? Why wouldn't it be 520 heads then? Right? We could just as easily flip and get 420 heads or what would it be? Or 580, right? Our best guess is 500. A die will be rolled 6,000 times. About how many aces are expected? So rolling a 1, 1,000, 1/6 of that. That's our best guess. In 5-card draw poker, the chance of being dealt a full house, 1 pair and 3 of a kind, is 0.14 of 1%. So 0.14%. If 10,000 hands are dealt, about how many will be a full house? So, okay, you've got, the idea is you've hypothetically got this data here, this 0.14% metric from, an infinite number of hands being dealt, right? Or you could do here you could do a counting analysis in this case, because if you're assuming the deck is fully shuffled and you're drawing at random, then you could actually do a counting analysis to get, you don't have to do an actual experiment in this case. You could just do an analysis and get the counts, right? Okay, and so the counts say that the number of ways that you could get 1 pair and 3 of a kind, the number of ways you can get 1 pair and 3 of a kind divided by the total number of possible hands is going to be about 0.14%. So 0.0014 would be the actual ratio. Okay, and so with that information, then, if you had to make a prediction about if 10,000 hands were going to be dealt at a Vegas casino over the next few months, or maybe even less than that, I guess, how many would you expect to be a full house? Well, you can make an estimate there. You could say, about 14. Okay, 100 tickets will be drawn at random with replacement from one of the 2 boxes shown below. On each draw, you will be paid the amount shown on the ticket in dollars. Which box is better and why? Okay, so all we can do is think about this from the, what are the, if we did draw an infinite, we're only doing 100 tickets, right? But if we did draw an infinite number of tickets, with replacement here, then we would expect to get the same amount of 1s and 2s. So half 1s and half 2s. So if we drew n tickets, which is like a trillion tickets, right? Then we would have n divided by 2 times $1 plus n divided by 2 times $2, which just, if you factor in n divided by 2, that just, it's $3 times n, right? $3 times n. Same idea here, but it's going to be $4 times n. Now you might say, well, but 100 tickets, you could draw a bunch of 2s here and a bunch of 1s here. Maybe, but if this is all the information you have, then this is your best bet. If you want to win the most money, this is your best bet.